Greetings, folks. Miss Wensitz here, and I am super excited because we have reached our last topic of AP Calculus BC. And even better news yet, our last topic is not the hardest thing we have done all year. So we are excited. So let's get into it because we got some pretty cool stuff coming our way. So, what we're doing in this topic is we are looking at functions that are representing power series and what all we can do with them. Okay? So, first thing I want to look at is what is the function, given the function sine of x, what is its derivative? Not a hard question. One that we have done numerous times. You are all confident in knowing this, and that is cosine of x. Okay. Now, I would like to think of this function a different way. I would now like to think of it as a power series. So we have a function, specifically it is a function sine of x, and we learned about this function in our last topic. That function can be rewritten as a power series from 0 to infinity of -1 to the nth power, because it alternates. And sine was the one with all of the odd powers. Well, an odd number is written as 2n plus 1. And it was all divided by the odd coefficient. The odd factorials. Well, if I write out a couple of those terms, that is the same thing as when I plug in 0, I get positive 1. I get x to the first over 1 factorial, aka just x. When I plug in 1, I'm going to get -1. X cubed over 3 factorial. When I plug in 2, I'm going to get positive 1, x to the 5th over 5 factorial, so on and so forth. Let's actually do one more. Negative x to the 7th over 7 factorial plus ... Okay? Well, functions. We can take derivatives of functions, so let's do just that. I'm going to take the derivative of my function, and specifically, I'm going to take the derivative of the Taylor polynomial that we have written it as. Well, when I take the derivative of this is just the derivative of x is 1. The derivative of x cubed over 3 factorial will be negative 3x squared over 3 factorial, positive 5x to the 4th over 5 factorial, negative 7x to the 6th over 7 factorial, ... Okay? Well, this is math class. What can we reduce? Well, we could reduce the 3 with the 3 factorial, and that's just going to turn into 2 factorial. I could reduce the 5 with the 5 factorial, and that will turn into 4 factorial. I can reduce the 7 with the 7 factorial, and that will reduce to 6 factorial. And holy smokes, folks, wouldn't you know it? We know this. That should look pretty darn familiar. What in the world is that? Well, that's just cosine of x. Pencil drop. Psh, mind blown. I know, right? Pretty groovy. So what does all that mean? It just means we can do all the normal stuff with power series and with Taylor polynomials that we can with any function. Okay, we can take derivatives. In fact, I can take derivative of the nth term. I can take the derivative of a series, all that great stuff. So let's go ahead and look at a couple examples and what these might look like on your AP exam. So example number 1 reads, let h of x be the function represented by the series given right there. Write the first 3 terms of the series of h of x. So this is just asking us to write out the first 3 terms. Okay? Well, start by plugging them in. If I plug in 1, I get x to the first over 1 squared, which is just x to the first. If I plug in 2, I get x squared over 2 squared, or in other words, x squared over 4. If I plug in 3, I get x to the third all over 3 squared, which is 9. And that is all it asked us to do. Okay. Now, one thing I should do, I need to change my equal sign to actually be an approximation, because h of x, if h of x is representing this series, then it would be the entire series. Well, if I'm just writing the first 3 terms, that means h of x is approximately equivalent to that value. Okay. All right. Now, it asks us, TV timeout, I am going to add one part to this. Let's also write the nth, or the general term, because we're going to need it in the next one. The general term, that looks weird, is simply asking if we were to continue this pattern, what is the pattern? All right, well, the general term is the series itself. That is just x to the nth, whatever term we are on, all over n squared. Okay. So now part B says write the first three terms and the general term of the series h prime of x. Well, to do that, all I need to do is just take the derivative. Specifically, I am taking the derivative of my function that I wrote up here with respects to x. Well, the derivative of x is just 1. The derivative of x squared, well, that's just 2x all over 4. The derivative of x cubed is 3x squared over 9. And when I take the derivative of the general term, keep in mind, folks, n is a constant. It represents whatever term we are on, the first, the second, the third. So when I'm taking the derivative of this is just power rule. This n squared is a constant, that n is a constant. So my derivative is going to turn into n times x to the n minus 1 all over n squared. And now at this point, all I need to do is reduce. So I know h prime of x is equal to, now I can leave equal to symbols here because I'm writing the general term, and I'm going to put my plus dot dot dot, so it goes on, is equal to 1 plus, we know 2 over 4 reduces to 1/2, 3 over 9 reduces to 1/3, and when I have n over n squared, that just reduces to x to the n minus 1 all over n. And there we have it. There is the function h of x representing that series, that power series. And we took its derivative. Not bad, right? Told you this wasn't the hardest thing we've done. All right, next example. Oh, sugar. I didn't space this out. I'll space this out for you. I apologize. This is why we proof things before we do it. All right, so for example 2, I'm going to use a post-it here for our notes. You'll have more space when you go to do these. For example 2, we are writing the first three terms. Well, first of all, note we are given the function. Okay, so a little different. We're not given the power series right now. We're given the actual function expanded out. Write the first three terms and the general terms for the series of f prime of x. So truly following the same thing that we just did, we are looking at finding the derivative of this function. Well, the derivative of 3x is just 3. Derivative of 2x squared is going to be 4x. Derivative of 5x cubed. Watch what I'm going to do here. I'm going to go 5 times 3. And I'm thinking you're anticipating why I'm doing that. And I think it just asks us to write the first three terms. So I can stop right there. And now I can write my general term. So let's get our plus dot dot dot. And then my general term, if I keep going with this, good old solid Post-its. Once again, folks, n is just a constant. So this -1 to the n plus 1 is going to stay there. That is a constant. Nothing changes with it. This quantity of n plus 2, that is still just a constant. Nothing happens to it. So there's no fancy product rule or anything like this. So the only thing I'm taking the derivative of is anything with an x in it. Well, that turns into n times x to the n minus 1. And that is all over n factorial. Okay? So in theory, what we could do is we could reduce all of this. So I have 3 minus 4x, and now do you see why I didn't multiply my 5 and my 3 together? This 3 will reduce with the 3 and 3 factorial to leave me with just 2 factorial. I'm actually going to write that over here so I have a little more room. So that term turns into 5x squared all over 2 factorial plus dot 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 plus, and this n will reduce with this n factorial to leave me with n minus 1 factorial. Oh, spacing. Spacing's an issue today. I apologize. N minus, not plus. I don't know what I said. I think I said minus. There is part A. Now part B I covered up, but you can see it on your page. Let k of x equal the integral from 1 to x of f of t dt. Right, the first three terms and the general term for k of x. So what are we doing on this example? On this example, we are now integrating. Okay, I am integrating what is happening here. Well, let's think about it. K of x is equal to the integral from 1 to x of f of t dt. All right, so I'm really looking at the integral from 1 to x of my function f of t dt. So my function is what I have given, there it is, given in the problem. Okay, I am integrating that. Well, when I integrate it, it's simply going to turn into, what's the antiderivative of 3x? So the antiderivative of 3x, add 1 to the exponent, divide it by your new coefficient. Okay, what about 2x squared? Well, add 1 to the exponent, divide it by your new coefficient. About 5x cubed over 3 factorial. Same thing. Add 1 to the exponent, divide by your new exponent. Then I can put my dot, dot, dot. And now this whole complicated mess, again, folks, we only care about the x term. All the rest is just part of our coefficient. So in fact, I can think of it as one ginormous coefficient. And I can think of the antiderivative as x to the n, add 1 to the exponent, divide by your new coefficient. And if we wanted to, we could clean this up. Nothing happens with the first two terms. 4 times 3 factorial is technically the same thing as 4 factorial. So that could be one alteration. And then this n factorial times n plus 1, that's really the same as n plus 1 factorial. So that could be written in that variation. Okay. So there we have it. All right. Next example. Hopefully you're hanging in there. Consider the series sine of x. So we've already known this. We've done a couple examples with it now. Let's ask ourselves, could I construct a series for sine of x squared? Well, if I wanted to construct a series, if I wanted to create a Taylor polynomial, well, we know to create a Taylor polynomial, we are just looking at derivatives. So let's think of this the long way. This is also good review for us. The long way says we need to find what our function is evaluated at c, which I'm just going to use x for this case. All right, well, then I have to start taking derivatives. Well, my first derivative is going to be derivative of the outside, so cosine of x squared, but then I have to chain on the derivative of the inside. Okay, not too bad. But now I got to keep going because I need to know my second derivative. I need to know my third derivative. So when I start to do my second derivative, well, now I just introduce product rule. So I'm looking at derivative of the first times the second. I don't know why I went to 2x. The first term here is cosine of x squared. So the derivative of cosine of x squared is negative sine of x squared. But then I need to chain on the derivative of x squared, which is 2x. So that all represents the derivative of the first times the second plus the derivative of the second, which is just 2, times the first. And as we see, if I were to keep going with this into the third derivative, well, I have product rule for that. This one is not, but when I go to take the derivative again, it's going to turn into product rule again. So these derivatives get really messy very fast, and then I end up getting into all kinds of chaos where chances are I'm going to make a mistake. So the question becomes, is there a better way that we can do this? All right, is there a better way that we can construct a series, for sine of x squared? Well, the answer is yes. Okay, we know we can based off of the fact that sine is one of our Taylor polynomials. We know how it expands. The only difference is we do not have x anymore. We are dealing with x squared. So basically what we are going to think of this as, I think I put it on the next page. No, I didn't. We're going to keep writing it here. Is think of it as just substitution. Sometimes if we substitute, it makes our life a lot easier. Let's let x equal t squared. Okay, if I let x equal t squared in my series sine of x, and then all of that jazz, oh goodness, it would simply turn into sine of t squared is equal to, well, it's just substitution, folks. Replace all your x's with t squareds. This is going to be the same thing as t squared minus t squared to the third over 3 factorial plus t squared to the fifth over 5 factorial minus t squared to the seventh over 7 factorial, which that turns into t squared minus t to the sixth all over 3 factorial plus t to the 10th all over 5 factorial minus t to the 14th over 7 factorial plus dot dot dot. And there you have it. We just made sine of x squared. We just made a Taylor polynomial of sine of x squared by simply using substitution. Which really leads us to a great conclusion that when we are dealing with power series, there are mathematical rules that they are going to follow. And those mathematical rules are basically saying follow your instincts. If we have a function that is represented as a power series, and we have a constant times that function, we can treat it as simply substituting our constant into our function. If our constant is k to the x, or in other words, if we substitute k to the x in place of x, well, we can distribute the nth to each term, and that turns into k to the nth, x to the nth. That is where it is coming from. So it really just means substitute k to the x in there. And the same holds true if we had x to a power, just like we did on the last example. It wasn't sine of x, it was sine of x squared. Well, if we plug that function in, that will replace x with x to the capital N, and we are still raising that to the lowercase n, which is the same exact thing as what this states. Okay, so basically all these operations are saying is substitute in whatever it is you are trying to find. Whatever it is you are trying to evaluate. Okay. All right, so example 3. Find a power series representation for the function f of x equals e to the x squared. So the first thing we need to recognize is what power series are we dealing with? And this is ultimately where memorizing those 3 power series, e to the x, sine of x, and cosine of x, becomes so important because this is a huge time saver. We no longer have to sit here and write out the Taylor polynomial and then substitute it in. I know e to the u is the same thing. I'm going to use u instead of x since x is what we're using in our problem. E to the u is the same thing as 1 plus u squared over 2 factorial plus u cubed over 3 factorial plus dot 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 plus u to the n over n factorial plus dot dot dot. Well, I am replacing my u with x squared. So when I plug it in there, I have 1 plus x squared plus x squared squared plus x squared cubed plus dot 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 x squared to the nth plus dot dot dot. And when I simplify this, I'm looking at 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial plus dot 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 x to the 2n all over n factorial. Okay? Not bad at all, folks. In the moment of truth, we have reached our last example for AP Calculus BC. Whew! Let k of x equal cosine of x squared. Write the first three terms and the general term of the power series for x times k of x. Now careful, I'm trying to trick you here. All right, so the first thing, I am dealing with x times k of x. We are going to address that x at the end. That x is going to have to get multiplied by our entire function. All right, now beginning with our function, we are looking at cosine of x. So let's write out what is cosine of x. Cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus x minus x to the 6th over 6 factorial. Now I'm really doing a lot more than I need to, but that's just because this is good practice for us, so we do not forget what our special series are. All right, but I don't want cosine of x, I want cosine of x squared. So in other words, replace our x with x squared, and we're looking at 1. And if it's okay with you, I'm going to go ahead and plug the x squared in and do that math at the same time. So x squared squared is x to the 4th. X squared to the 4th is x to the 8th. X squared to the 6th is x to the 12th. And x squared to the 2n is x to the 4n. Okay? We're not done though. Why are we not done? We are not done because the function, or excuse me, the question asks us to write the first three terms and the general term of the power series x times k of x. We just found k of x. We want to know what x times this is. So in other words, all I have to do is multiply x by the series that I just found. And since I only need the first three terms and the general term, I'm only going to write those first three, and then we will actually distribute. There's my first three. Let's get the nth term still in there. And when I distribute this, I am looking at x minus x to the 5th all over 2 factorial plus x to the 9th all over 4 factorial. And my general term, let's actually separate this with a comma because it asks for the first three terms, which is what we have here. My nth term will be negative 1 to the nth. And when I times x by x to the 4n, careful here, x times x to the 4n, multiplying bases, we add exponents. So that turns into x to the 4n plus 1 all over quantity of 2n factorial. And there you have it, folks. We just determined what the power series of x times cosine of x squared is equivalent to. So if I wanted to evaluate this at 2, I could by simply plugging 2 into that problem and doing some basic math. Oh, folks, I'm so happy. I hope you're happy. You should be so proud. It has been a long year. It has been a challenging year, but you guys have hung in there and done a great job. And for that, I applaud you. I applaud you tremendously. Oh, so much for having this all queued up. Come on. Woohoo! Do the Carlton, folks. Please be careful when jumping off furniture. It is not recommended. And do not throw your papers in the air until you are done with your AP exam. Thanks for watching. This is Miss Wensitz officially signing out. And what do I have? Oh, I should have come more prepared. Oh, I am prepared. Miss Wensitz always has food. For you this time, we got a whole bunch of cookies. Yep, that's right. We got the family size deluxe chips, rainbow style Keebler M&M cookies. Enjoy.